7 years experience in mining industry, mainly in porphyry and copper deposit. So today I will be your moderator for this session. So as you can see here, this is our roadmap for our geometallurgical workshop. Now we are on part 3, estimation of geometallurgical parameters in the block model, which is initially we plan to do it for 1 month after part 2. But yeah, due to the schedule, we can make it in December. And then for part 4, sorry for busy noise. And for part 4, most likely we will conduct it on January 21 or February to 21. Uh, we will announce the schedule mainly on LinkedIn. So if you are interested, you can keep in touch with us through LinkedIn or look at our LinkedIn profile. So we will also upload the part 1 and part 2 recording video and then the presentation slide to YouTube and Google Drive. So yeah, once again, we will announce it in LinkedIn. So this is our speaker for today, Cristian. I think Cristian is here already. Cristian, can you turn on your microphone? Okay. ¿Cómo estás, mi amigo? You feeling good and ready for this session?
Yes, my friend.
Okay, sounds good. So Cristian is a senior geometallurgist. Currently, he is working at Wood PLC Chile with 20 years experience as economic geologist. His specialization is modeling in geology and geometallurgy, and also doing data analysis and project development. He is also a competent person for NI 43101. This is our agenda for today. We'll have an opening from me and then presentation. It will be presented by Cristian, project development, and then at the end of our session, we will have like 20 minutes for question and answer. So if you have a question, mainly you can simply turn on your microphone on once we enter this session, the question and answer session. But if you don't want to talk, you can simply type your question down on the chat section. So this is our roadmap. First, we're gonna talk about estimation method. We will not cover like too detailed or too specific of particular method, but we will talk about the concept. I pretty believe that all of us is pretty familiar with this kind of method: rigging, linear regression, imputation, inverse distance, and anything else. Yeah, so instead doing the specific things, we're gonna talk only about the concept. It's just only for refreshing. And then Cristian, we're gonna talk about sampling limitation, determine the estimation method, and then project development once again in Orange data mining. For you who just come for this part, I mean, you didn't attend the previous one, we use Orange data mining for showing the demonstration for project development. And then the result is we will obtain an estimated geometallurgical parameters. Okay, so I will talk about kind of method that we can use to do estimation for our geometallurgical purpose. The first one is imputation. So as you can see on the right hand side, we have two variables here, x and y, and we have one missing blank value. So the question is how we fill out the blank. So by using this imputation method, mainly we have three ways. The first thing is we can remove it, easily remove it, but yeah, for estimation, we don't want to remove our data, right? And then the second one is replacing with random variable. The problem with this, if we replace our data with random variables, it may be biased. I mean, if the random variable is really high or really low, it will change our distribution. So instead doing the first two, removing and replacing with random value, we can use mean substitution. Any other option is fill with mode substitution, but in this case, we will use mean substitution. So as you can see, we have two variables here, x and y, right? So we put x and y in a scatter plot. And as we can see, our data here is really scattered. And the coefficient of correlation is showing no correlation with R value is 0.05. As we know together that if our data is strongly correlated, the coefficient of correlation will showing number 1 or -1. And if it is not correlated at all, the result will be 0. So here, it will be meaningless if we considering x value if we want to fill the y value. So instead considering x, we just need to make a substitution with calculation of mean value from y variable. So here to fill out this blank, the yellow box here, we just need to make a mean calculation or average. And then we will get the result of it. The next one, I believe all of us really common with this one. We have two kinds of variables here, x and y. And then the same question, how we fill our data, fill the blank data. In this case, our data is strongly correlated, right? With R value or coefficient of correlation value is almost 1. This one is 0.97. It is strongly correlated. So in that sense, we can use our x variable to predicting our y value here. So as we know that the single linear regression equation will like y equal to a, where a is intercept of our data, and plus b times x value, and we get the result that a is 0.2 here, and then b is the slope of regression is 1.4. 1.4 is obtained by dividing y value divided by x value, 1.4, and then we just need to multiply with our x value on row 9. So the result is 1.012. That's how we uh, estimate the data, the blank data. The question is how we estimate something that considering spatial relationship, right? So we are interested to know whether our data is has spatial relationship or not, right? So basically what we did is pretty similar with linear regression. We put our data into a scatter plot, but here we will considering spatial relationship. So this is kind of illustration of spatial relationship. If we have zero or if we have a initial sample point, for example, 0.0 here, and then we have two other sample here, x, y, xi, yi, and then xj and yj. In order to get the distance between tj and ti, we just need to make a calculation like xj minus xi and then yj minus yi. So in that sense, we could obtain a distance. Okay. So this is the concept of sample pairs. You know, in variogram we talk about sample pairs, right? So this is an illustration of sample pairs. For example, if we have 36 amount of samples, it is indicated on X on the my left hand side. We have 36 amount of samples, and we are looking the pairs of our sample in particular direction with particular spacing. In this case, we are looking to the north, and then with 1 meters sample pairs. You can see that it will pairs with with sample location, and then we will obtain 30 sample pairs from it. And then if we increase our spacing for sample pairs, for example, we have 2. For example, if we use 2 meters, we will have a decreased amount of sample pairs. In this case, we will have 24. So if we increase our sample pairs, we will get lower amount of sample pairs. So this is for example, if we have a spatial distribution of 100 samples here, and then we do exactly the same what we do on previous one, like this, we are looking for sample pairs in particular direction, we will get 90 amount of sample if we are looking with spacing 1 meters. We will get less amount of sample, it will be 80 if we are looking for 2 meters, and then if 3 meters it will be decreased to 70, and if we are looking in north direction with spacing 4 meters, we will have 60 amount of samples. So for x-axis, this is called as H scatter plot. Previously on linear regression, we put x-axis for x variable and y-axis on y variable. The concept for this spatial relationship is pretty similar to a linear regression. Actually, it is a linear regression. But the thing that we put on the scatter plot is on x-axis is value of our initial data, and then on y-axis is value on our specific sample pairs. Okay, so for example, if we have this 0.0 initial data, 87, it will be paired with 77. Okay, so if we put it on this H scatter plot, as we can see that coefficient of correlation will be decreased with increase of distance. So as we can see, coefficient of correlation with distance 1 is 0.74, and with distance 2 meters is 0.59, and 3 meters 0.56, and then for 4 meters is 0.48. So any other thing that we can observe is the more our distance increase, the more dispersed our data. As you can see here on distance 1, our data pretty stick to our regression line. This is line r equal to 1. And then if our search for sample pairs is increased, the data is more dispersed. So basically to identify or to indexing how dispersed our data beside coefficient of correlation, we can use covariance and variogram. So as you can see here, if we plot our coefficient of correlation, the coefficient of correlation value on y-axis and then the search distance on x-axis, we will get this kind of result or this kind of graph. The more distance increase, the lower value of coefficient of correlation we will get. The same thing happened with covariance, because the formula of coefficient of correlation is covariance divided by standard deviation. So the result will be similar. The more distance increase, the lower amount of covariance we will get. But for semi-variogram, it's like a vice versa of covariance. If our searching direction or searching distance increase, we will have higher amount of variogram. As we can see here, in distance 1 is about 300 and distance 4 is more than 600. So basically, this is why we need to observe our data, because this semi-variogram, as we know together, that it able to identify range, seal, and nugget effect. So in this case, if we put zero distance, the result of semi-variogram will be 0, right? But in real case, we don't use specific direction. I mean, not absolute direction, not like 1 meter, exactly 1 meter. We use like tolerance, right? Like searching tolerance 20 degrees or 30 degrees from our interested direction. So in that sense, nugget effect will be caused or will be appeared by sampling error and short scale variability. So that's the thing that we need to do before we choose our estimation method is check if our data is strongly correlated or not correlated at all. So if our data is strongly correlated, we can easily choose kriging or what's the name of it? Inverse distance or nearest neighbor on any other method. But if our data is not spatially correlated, we just easily can use imputation or linear regression, either single linear regression or multiple linear regression. So yeah, I think Cristian will talk about this one, sampling limitation in geometallurgy and its impact on block model estimation. So yeah, Cristian, can you turn your microphone on?
Yes.
Yeah. Okay.
Sure.
Yeah, you can.
Yep.
Yeah.
Okay. First of all, hi everyone. It's a pleasure to me being here with you in this event. Now, please let's talk about a key topic regarding its usually limited amount of data. First of all, something to bear in mind. Please go ahead. To bear in mind, Abdul?
Yeah.
Please go ahead. Next.
Yeah.
Perfect. Okay. To bear in mind, non-model reproduces the reality in a perfect manner. Okay, to bear in mind. Then, uncertainty is related to a lack of information. This is particularly important in estimation of geometallurgical parameters, and it is due to, firstly, geometallurgy typically requires large samples with a particular granulometry, usually H. Secondly, geometallurgical characterizations imply high cost related with metallurgical, assay, physical, and mineralogical testing. As a result, the number of geometallurgical data is usually low compared with assay data. Okay, so this is very important to bear in mind. Please, next. Okay. Uncertainty. Uncertainty may bring about significant deviations and, as a consequence, losses for the business. A delicate balance between defining a sufficient number of samples for controlling uncertainty and cost of geometallurgical characterization needs to be reached. Next, please. Abdul? Okay. Next. Connection is being a little bit slow. Okay, as discussed in the part 1 of our workshop, geometallurgical characterization should be considered from early stages in mining projects. First, characterizations during scoping and pre-feasibility level will allow a preliminary understanding of the relationship between metallurgical and geological features based on the geological knowledge of the deposit. It is crucial also identify the key parameters that might influence the metallurgical performance. For instance, mineralogical testing will permit understand mineral association of species, grain size, and liberation. Assay will give us information about deleterious element that potentially might be part of concentrates. The next, please. Okay. Okay, factors that influence sample requirement. Firstly, geological control on the metallurgical parameter. In some deposit, geological domain exhibit a strong control control on a metallurgical sample comminution, but only weak for others, such as metallurgical variables with strong control determine a less sample requirement for geometallurgical characterization. Okay. Secondly, variability of metallurgical parameter in geological domains. Metallurgical parameters may express high or low metallurgical variables with high variability will require a higher amount of samples for geometallurgical characterization. And finally, some parameters display clear spatial continuity, which allow modeling through variogram, as Abdul explained previously. Metallurgical variables that show clear spatial continuity will require less amount of samples for geometallurgical characterization. The next, please. So please take a look a moment on this chart. This chart is about the scenarios for geometallurgical sample requirement. This is very important concept for the reasons we previously talked. The lower one of samples of geometallurgical data. Okay, this chart displays in the horizontal axis which is weak or strong. The vertical axis shows the variability of the metallurgical parameter in low or high. Okay. Okay. And rectangles inside the boxes represent geological domains showing the variability of metallurgical recovery. Okay, in this example is recovery. The range of metallurgical recovery is indicated by the numbers on the right top and bottom of each rectangle.
Hola, Cristian. You are disconnected?
I came back.
Okay, cool. So please continue.
Okay. Where is the other people? Is there?
Yeah, we are still here.
Okay. Okay, because I only see your icon. So, okay.
Yeah.
Okay. Sure, everyone. All the other people is there?
Yeah, yeah.
Yeah, we're all here.
Yes,
Okay.
I'm here.
Yeah.
Thank you.
Yeah, you can continue,
Okay,
Cristian.
Okay, sorry for the interruption. Well, I was saying that the rectangles inside the boxes represent geological domains showing the variability of metallurgical recovery. Okay, the range of metallurgical recovery is indicated by numbers on the right top and bottom of each rectangle. So, in a first scenario, show a box. Metallurgical recovery expresses high variability as you can see, and a weak geological control. As a consequence, will for the red color. A second scenario is represented by orange boxes, this diagonal, which will require a moderate amount of samples for geometallurgical characterization. In the bottom left box, metallurgical recovery is slightly controlled by geological domains, but exhibit low variability, which is good. On the contrary, in the top right box, geological control of the parameter is strong, but this shows high variability. Scenario showed in the green box, metallurgical variable is strongly controlled by geological domains. In addition, it displays low variability. Therefore, sample requirement will be the lowest. Okay. I would like to ask if we can continue. Yes? Okay, please go ahead, Abdul. Now, what are the sources of weak geological control for metallurgical parameters? Firstly, a lack of quality if the quality of logging, for instance, logging is poor, we will obtain a geological model of poor quality that not control the metallurgical parameter. The same occurs if our metallurgical testing or assay not fulfill the right procedures. Secondly, incorrect EDA. As discussed in the part 2 of our workshop, the correct definition of units through an exploratory data analysis is a key stage for the estimation of metallurgical parameter. And thirdly, the nature of the metallurgical parameter. Some metallurgical parameters do not express high variability. For example, copper recovery in ores from primary zone in porphyry deposits typically shows variabilities as low as 2 or 3% expressed as coefficient of variation. The next one, please. Okay, so type of approach for block model estimation. This flowsheet will help us to select the best approach. From the left, the quality of the approach decreases. It's shown by the purple arrow. So the quality also decreases the number of samples required and the cost of characterization. As the project moves to a more advanced stage, we should move in the chart from the right to the left. Okay, about the flow sheet. First, if the metallurgical parameter shows spatial continuity, that's the question on the top box, and an appropriate variogram can be obtained, the best option is Kriging or equivalent. In this manner, we will take advantage of the spatial correlation of our data, as Abdul explained previously, which is expressed through the variogram. Secondly, if the data does not show a clear spatial continuity, a regression model can be built based on the statistical correlation between the variable of interest and other variables called predictors, such as mineralogy, assay, etc. As a third option, if the result of our correlation is not good, in other words, if the coefficient of determination R squared of our regression model is low, then we can just impute the mean or median or mode of our metallurgical by each geological domain. Okay, please, the next one. Okay, this is the final product of our estimation will be a block model. In this case, for the metallurgical variable A cross B. Okay, so this is a actual block model showing the intervals of A cross B, which is a comminution parameter. Okay, please. Okay, let's move to our project for today. What are we going to do now? Okay, let's make a regression model in orange data mining. The goal of our project is develop a regression model for acid consumption, okay, based on assay and mineralogy. And dataset is the same we used in the session 2, but no worries, you want to show and explain the dataset. And for validation methodology, we want to use this train testing method with 80% of training set and 20% of testing test. We're going to explain this later. Please go ahead, Abdul. Okay, this is the dataset to be used in our. It contains 50 and about 200 samples or rows. So the number in the first column are the samples, and the columns are the variables. Variables are divided by type and colored. So the first type corresponds to the sample number. Okay, sample number. Variable y coordinates. In orange, 3 types of acids: carbonate, iron, and sodium. In purple, mineralogy, okay, like gang, totaling 100% of the rock. Finally, the metallurgical variable to acid consumption, which is our target variable. In other words, what we are interested in modeling. So this is our dataset. Please take a look on this. So acid consumption, this is our target, acid consumption. The next one, please, man.
Okay, so Cristian, are you okay if I talk about this one? As we
please go ahead.
Okay, So basically, as Christian mentioned before, even though we have decided we will use this regression approach to obtain our metallurgical parameters, or to estimate our metallurgical parameters, we are still trying to identify does our data fit if we want to make a kriging or any other estimation or not. So the first thing that we need to do is we conduct a statistics. The idea of this is we should identify we can check whether our data is stationary or not, because as we know together that stationarity is mandatory if we want to make an estimation using kriging, right? So here, as we can see, our global mean, as we can see together from our 196 data, the mean is about 20 point something, and the variance is 189. And if we try to randomly check our data, for example, in this one, we use amount of data is 40. As you can see, our data is very different. For the purple box here on the left side, you can see the mean is only 12 and variance is really different with the variance for global data. The mean is only 12 point something, and then the variance is 50. And then if we look on the green box, the mean is 32 and the variance is 237. So in that sense, our data is not stationary. So it will be it will bring a problem if we force our data to be estimated using kriging, because the result will be not reliable, should I say. And if we look about the variogram, we put all of these 196 samples, and we put it on the variogram. As you can see, our variogram is really scattered and not showing the correlation. As you can see here, in the closer distance, the variogram is high, the semivariance value is high, and then it will decrease again, and then it will increase and then start to be scattered. So even if we try to fit it with a variogram model, in this case we use spherical variogram, it doesn't fit. So that's why in this case we prefer to use linear regression instead of doing kriging, because our data is not stationary, and then our data is not spatially correlated. But in the real case, if your data is strongly correlated, you can easily choose kriging and doing estimation in your own software. But once again, if your data is not correlated, it's strongly suggested that you avoid kriging or inverse distance, and then choose imputation or proxy or linear regression. So that's the thing. Christian, can you continue?
Thank you, man.
Okay,
thank you.
Cool, thank you.
Okay, so after reviewing those important concepts and data set, let's check the concept of our target variable for the model, for the regression model, which is the acid consumption. Okay, this is a scheme, an illustration for the test. It's a metallurgical testing. Okay, this parameter is obtained from a metallurgical laboratory test named bottle roll test. in this test, 1 kilogram of sample, 100% under 2 millimeters, is put into a plastic bottle with 2 liters of acid solution. The bottle, as you can see in the illustration, spins, in this case at 20 RPM. The acidity, the pH, is kept at 1.5, the pH, adding sulfuric acid when required. Obviously, the sample is consuming acid, and then we need to add continuously more acid to keep this pH at 1.5. Finally, with all these additions, we can calculate the acid consumption of the sample. One important topic we need to bear in mind, this is an important parameter for the hydrometallurgy, because sulfuric acid corresponds to roughly 10% of the OPEX in a leaching plant. And the cost of this input is about around $100 per ton. Okay, so this one, the acid consumption, is an important reagent for hydrometallurgical operations. Okay, and the next concept for finishing is the validation methodology. Okay, for the validation methodology for our linear regression, we're going to use this train test split. What is it about? Okay, please look at the illustration. Look at this flow sheet with the initial data on the top. After that, a data splitting and obtaining two data sets. Okay, so the important thing to bear in mind in here is trained model must perform well on new unseen data. In order to simulate the new unseen data, the available data is subjected to data splitting, whereby it is split into two portions. Okay, 80% of the original data is used as the training set, and the remaining 20% is used as the testing set. Okay, and we are ready. We finish presentation, and let's move to our project. Okay, Abdul?
Yeah.
I'm gonna take the control of the presentation now, if you
Yes, please.
agree.
Yes, please.
Okay. So please tell me if you able to see the software.
Yeah, we can see the software.
Yep, all good here.
Perfect. Okay, this is new for maybe for some of you. We used this software previously, but again, let's talk briefly about this software. Let me introduce you to Orange Data Mining. This is Orange Data Mining, okay? Orange is an open source data visualization, machine learning, and data mining toolkit. Orange components, this one, all of these beautiful things in here, are called widgets, and they range from simple data visualization, subset selection and preprocessing, to empirical evaluation of learning algorithm and predictive modeling, which is our task for today, predictive modeling. Orange consists of a canvas, this white part, and interface, this one, onto which the user places widgets, like this one, okay, and creates a data analysis workflow. Let's start with import our database. Okay, so we can just drag it, okay, drag it, or just right button, and it's really simple to use. We can move our widget as we wish. I'm gonna make a zoom like this. Okay, and okay, let's double clicking here in file. Okay, so this is how we upload the data, load the data. This is our data, acid consumption, okay? And we have these columns. And first column corresponds to the name of the variable, okay? As we can see, they are the variables previously reviewed: coordinates, assay, mineralogy, acid consumption, okay? Can you see my pointer?
Yeah, we can see it.
Okay, perfect. So the second column is important because it represents the type of variable. In our case, all the variables are numeric type, but obviously we could have categorical, text, even datetime, sorry. But in this case, our variables are all numeric. Okay. Finally, the third column represents the role played by each variable. Sample is considered metadata, okay? Because we don't want this variable to be part of the analysis. We can, in this case, in this exercise, we can skip, not consider the coordinates in this case. And that's it. All these are features we want to use for the regression as predictors, and our target variable is not part of the target function. It's here, it's acid consumption, okay? We apply here and close. Okay, let's move. Make a link just with the left button in your mouse, and we have different options. In this case, data table. So data table will allow us to check the imported database dataset. Double click, and we can now check our data. Look at this. As Abdul indicated, 196 samples. 196. So look at observe the colored, the gray is the target. Remember the target variable, which is acid consumption. The second is the metadata, the sample, not being part of our analysis. All other are features, okay? Features. The length of the var is a representation of the relative magnitude of each instance. Okay, so we have acid consumption, carbonate, iron, sodium, and minerals. quartz, feldspar, cerussite, jarosite, and siderite. Close this one. Okay. Remember our validation methodology. We want to use this testing split. So we want to use a widget for split our data, which is called data sample. We can, as you can see, we can take this option to take from here, from this list, or just drag it from here. Okay, it's the same. Okay, now we have our sampler. Oh, we need to correct this one, the entire data set. Okay, let's do this double click. What we have in here, we have different ways of sampling. Okay. In this case, we want to use 80%. Okay, 80 and 20. Obviously, we can move it. And there are other methods for sampling. We want to use a random method of 80% of our data. Okay, and let's see what happened. We want to have, remember, two data sets. This one, this one. What is this? Double click. Okay, now we have 157, which is, as you can see, more or less 80% of our original data set. Okay, so let's rename this one as what could be training. Okay, training. Name of this database. What about this one? Double click. Double click, and oh, we have a problem. Houston, 157. But we need to have in here our other 20%. So let's double click in the link in here, and can you see? We need to select the remaining data. Remaining data, remove this one, this connection. Okay, and now we have 39. Okay, this is our testing for validation. We are ready to make our model. Okay, so let's do our model, and what we're gonna do, we want to make a linear regression, this one. Okay, as you can see, we have this window explaining what we are doing. And if you right click, you have help option, as you can see. This is the help. It's really simple, really useful. Okay. We are almost done. So okay, linear regression. This is our linear regression. okay, algorithm. And it's ready. It's done. A new data table with the result of the regression. Double click. And we have now the parameters for our linear regression. The A, as Abdul indicated, is the intercept, and all the coefficient for our multiple linear regression. Okay, we are ready, except for we have not validated this one yet. Let's validate it. How? Okay, rename this one. This is testing. Am I right? This is for testing. So this is our data set, remember, with 39 cases or samples. Okay, let's use the predictions. With this widget, we can simply connect our model. Okay, that's it. This is our model. With this widget, we can make a prediction with new data, which is this one, or data you want to consider for your future investigations. Let's have a look with the scatter plot for finishing. This is our last widget. This is scatter plot, and let's see how it works with new unseen data. And that's it. Not too bad. And maybe it's an option we can just use our regression model for populate our block model. So in this case, the estimation is a regression based on mineralogy and assay. Okay. And maybe I'm not sure if you can see it, but if this is R equal to 0.85. So it's like more or less 0.7, 0.70, sorry, or 0.7 of as R squared, which is quite good indeed. And I think we have finished. So that's it. I'm gonna come back. Okay, man. Abdul, please take the control.
Okay. So yeah, I think the idea here is we get a parameters, and then we can use that parameters in our software. I mean, yeah, if we have that kind of parameters, right? And then we edit a script in particular software. For example, yeah, for example, in Leapfrog, we can edit that parameters and then edit the script in Leapfrog for our estimation. The thing is, why we don't show in Leapfrog or any other kind of survey software like Micromine or Surpak or Vulkan, simply because we don't have the right, we don't have the license to show it. So that's why we don't show it. The thing is, hopefully you get the idea where you get the parameters to edit the script. And then, yeah, once more I said, if you get the spatial relationship, you can skip all of this part, and then you can easily go to Kriging method that available in the software. So yeah, I think now we going back to the presentation. Can you see my screen right now? Can you see my screen?
Not yet.
No.
No?
Not yet.
Not yet. Wait a minute. How about right now? No? Still no?
Um,
No?
but maybe I can if you can.
Yeah. Yeah, I think the last part is about only about conclusion, and then we will have a question and answer. So yeah, if you can show to the participants, Christian, about the conclusion, maybe you can easily talk about it.
Okay. Um, Screen 2, this one. Yep. So conclusion is just as we previously discussed, the type of approach for estimation will depend on variability, geological control, and number of samples. This is very important. Our message for you, for all the audience, is usually considering the number of samples, variability, geological control. It's not necessarily the same as the assay estimation. There are sometimes some complications or particularities for estimate geometallurgical parameters. Other message is estimation of geometallurgical parameters needs to be included in the early stages of project development. So if not, we can obtain a project with serious, unpredicted, unseen problems, drawbacks. So that's our message, and thanks to everyone. Thank you for sharing these minutes with us, and please feel free for this discussion.
Yeah.
Have any question, comment?
So yeah, now we are on question and answer session. If you have something that you want to ask or something that you want to discuss, you can simply turn on your microphone. Or if you don't want to talk, you can just type it on the chat section. So yeah, Christian, while we are waiting for someone asking or someone to discuss something, I want to ask a question. Since our data it's not too much in early stage of the project, shall we say, and then yeah, maybe we only have like one sample for each domain or something. What is your suggestion for that? I mean, yeah, even if we don't have any metallurgical data, for example, what we can do for geologists during this early stage of our project? Yeah.
Okay, that's a really good question. Let me process because it's important.
Yeah.
Okay, I think if we have only few amount of a fistful of samples, or even we don't have any samples in early stage of exploration, still we can have this mindset of thinking in the in the mining, in the process as a chain. Okay, so we need to consider that hopefully one day this material going to be processed in a plant. It will produce some products for humanity, for mankind. So we need to take bear in mind that with our logging, with our ChemScan assay, we have probably enough information to make a preliminary idea of the potential impact of our material in geometry. For instance, imagine we have a copper deposit. We are evaluating a copper deposit, and in this deposit we have logging, we are ChemScan, optical characterization, and assay, and we discover that most of our copper is deposited in sulfur salt, energite, tetrahydrate. So this is a very important matter for processing, because if you want to generate a concentrate of that material, probably that concentrate going to reach over 0.3, easily 0.3% of arsenic in the concentrate, which is a problem. This deleterious element, this arsenic, for instance, could be a real challenge for the people in marketing. So we need to consider in early stages the mindset of processing. Even if we don't have, if we have no testing at all, still we can understand, based in our understanding of geologists or engineers, we can have a preliminary idea, as I said previously, of the potential impact of our material in the processing.
So in that sense, we can make a, what should I say, domain, like preliminary domain, something like that.
Yeah, exactly, man. Yeah, you're right. Maybe there are some zones with sulfur salt, but other with chalcopyrite. And chalcopyrite is clean, thinking in processing, in concentrate, clean, potential clean concentrate, but the other is potential complicated, should we say, concentrate. So yeah, you're right. Maybe this is a good approach. Make a preliminary domains for metallurgists, thinking, oh, okay, man, we have these two scenarios. Let's manage, let's test it in the future. But the good news is geologists warn us about these two domains. So maybe we can generate a plan for face this challenge.
Okay, cool. Thank you, Cristian. Really clear explanation. So, someone want to ask a question or want to discuss something, maybe? Okay. I think, yeah, everyone is clear about what you said, Cristian. So I think we can end our session. Once again, thank you for Cristian for sharing his time and his knowledge to us, and thank you for all of the participants who stay in this session and then sharing your time with us. Thank you very much. And yeah, if you have any question or further question or want to chat something with Cristian, you can easily drop a chat to Cristian's LinkedIn profile. So yeah, once again, thank you very much. Have a good weekend, everyone. Muchas gracias, Cristian. Que tengas buen fin de semana. Okay, see you
Gracias.
on any other question. Bye-bye. Have a good day.
Thank you, everyone. Bye-bye. See you.
Gracias, Cristian. Muy buena presentación.
You're welcome.
Hablamos.
Bueno, Cristian, un gusto saber de ti. Cuídate.
Gracias, Rodrigo. Igualmente. Obrigado.
Vale, chao, chao.
Chao.
De nada.